Greetings everyone and welcome to today's webinar, Different Approaches in Estimating Measurement Uncertainty. Great to have you here all with us. I am Arta Lamania, the Account Manager of Quality Management Systems here at PECB and the organizer of this webinar. This webinar will be presented by Bahar Hosizadeh, PECB Certified Trainer and Sales Manager and 17025 Consultancy Project Manager at PQP Limited. Please feel free to write your questions and comments in the question box in the right-hand control panel, or you can use the raise hand function. We will unmute you and you will have a chance to ask the question directly to Bahar. Bahar will answer to all questions accordingly at the end of the presentation. Please, Bahar, you may continue with the presentation.
Hello everyone, this is Bahar. I hope you all have a nice day. Today I'm going to talk about measurement uncertainty and different approaches for estimating the uncertainty in laboratories. First, I would like to introduce myself. Since 2005, I have been involved in ISO IEC 17025 training and consulting services, and I have undertaken more than 50 laboratories accreditation projects in different industries. I have also conducted more than 200 training courses in the field of laboratory accreditation, and I'm also involved in organizing proficiency testing programs since 2012. Now I'm going to start the presentation. First, let's have an introduction about the measurement uncertainty. A measurement result of a laboratory is an estimate of the value of the measurement. So the quality of this estimate depends on the inevitable uncertainty that is inherent to the measurement results. When the laboratory is going to report the result of a measurement, it is obligatory that some quantitative indication of the quality of the results be given, so those who use it can assess the reliability of these results. About the measurement uncertainty, the word uncertainty means doubt. So the uncertainty of measurement means the laboratory is not sure about the value that the laboratory is going to report. Uncertainty of measurement is a parameter associated with the result of a measurement, which characterizes the dispersion of the values that can be attributed to the measurement. As we can see in this picture, this is the value that laboratory is going to report. And this uncertainty value, which shows the dispersion of the values, can be reported with the measured value. So, to know the uncertainty, it's important to know the error in the laboratory very well. Error and uncertainty are not same topics, and they are not synonyms, but they are completely related to each other. First, let's have some introduction about the difference between error and uncertainty. As we can see in this picture, error is defined as the difference between an individual result and the true value of the measurement. This is the true value of the measurement, and this is the measured value. This difference, this value, is laboratory error. But when laboratory is reporting the measured value, the laboratory is not sure about this value. So this uncertainty is shows with this plus minus uncertainty value around this measured value. The measurement error, as we talked before, is the quantity value, measured quantity value minus a reference quantity value. This measurement error is defined by two different kind of errors. First is systematic error. Systematic error is a component of a measurement error that in replicate measurement remains constant. When the laboratory performs replicate measurement, this systematic value, this systematic error remains stable. It doesn't change. So it doesn't matter how many times the laboratory repeats the measurement, this value stays stable. But the laboratory can identify the causes of this systematic error. And when these causes can be identified, the laboratory can use correction. So this systematic effect on the measurement can be reduced or removed. The other part of laboratory error, measurement error, as we can see in this slide, is random measurement error. Random measurement error is a component of a measurement error which in replicate measurement varies in different manner, in unpredictable manner. So when the laboratory performs a test in very same condition, the same equipment, the same environmental condition, the same operator, the laboratory sees the different results. Everything is the same, but the values, the results are different from each other. The main reason of these differences and this dispersion is random measurement error. As we can see, this random measurement error varies in unpredictable manner. The laboratory cannot predict the random measurement error. The effect on the result is not the same. The reason is that the random measurement error cannot be identified. The reason, the sources of random measurement error cannot be identified by the laboratory. So the laboratory cannot remove this measurement error while performing the measurement. So we should see the effect of this measurement error in the uncertainty. In this picture, we can see the relationship between error of measurement and uncertainty. This picture shows this relationship very well. As we can see, here we have the uncertainty and here we have the result. As we discussed, uncertainty is the value that is completely related to the result that the laboratory is reporting. So we have measurement errors. As we talked, we have two types of measurement error. First, systematic error, and the other one is random error. Random error, as we discussed before, the laboratory cannot remove random error. So the laboratory cannot do anything to remove this error in the laboratory result. The effect can be seen in the uncertainty. So one of the main sources of the uncertainty in the laboratory is these random errors that cannot be removed during the measurement. But here we have systematic error. Systematic error, we have known systematic errors. For example, the laboratory knows that when they are performing some calibration, the laboratory notices that there are some differences between the true value and the measured value. So the laboratory performs some kind of correction to remove this kind of systematic error. For example, during the routine analysis, this error will be considered in the measurement results. We have two types of results here. First, the result before the correction, and then this result that laboratory is going to report is the result that the correction has been made on it. So here, when we remove the systematic error, there is no effect on the systematic error on the uncertainty. This systematic error can be shown in the result. The effect is shown in the result. But here we have some remaining errors. There are some systematic errors that laboratory is aware about these systematic errors, but the laboratory does not remove them or sometimes cannot remove this systematic error. For example, consider the laboratory is using a certified reference material for analysis, for calibrating an equipment. This certified reference material has a certified value, but this certified value has the uncertainty. But the laboratory used the certified value in the certificate, and this measurement uncertainty of the manufacturer of the CRM cannot be considered in the laboratory results. So this uncertainty of the manufacturer of CRM should affect the uncertainty of the laboratory. Or there are some other remaining errors. For example, the laboratory is performing some volumetric measurement in the laboratory. All the volumetric glasswares are calibrated in 20 degrees Celsius. But the working temperature of the laboratory is, for example, 23 or 25 degrees Celsius. This difference temperature in the laboratory cannot be corrected every day in the laboratory because it's very time consuming. So this effect will be seen in the uncertainty. This picture shows the relationship between error and uncertainty. As I said, error and uncertainty are different approaches, but they are completely related to each other. The sources of uncertainty, as we talked before, there are two main sources of uncertainty. They are from random errors or systematic errors. For example, during the sampling, laboratory can see some uncertainty. For example, the sampling method, sampling equipment, the person who performs the sampling, or some sources of uncertainty are related to the analyte. For example, the composition of the analyte, during the analysis, the efficiency of extraction phases, or as we talked, the reference analytical standards that laboratory is using, or matrix effects of the sample. These items, or for example, the environmental condition of the laboratory, or some working condition in the equipment, for example, different columns or different batch of CRMs, the sample itself, they are all the sources of uncertainty. And also we have other sources of uncertainty. For example, the laboratory is using some equipment, balances, thermometers, weighs for checking the balances. All of these reference standards have been calibrated before in the calibration laboratory, and all of them have uncertainty. That, as we discussed, these uncertainty values cannot be seen in the laboratory results, so the laboratory should consider these values in the measurement uncertainty. So after we know the sources of uncertainty, we should give some value to this uncertainty. It should be quantitative value. So the laboratory should perform some calculation to estimate the uncertainty. Generally, there are two different approaches for estimating the uncertainty. First is bottom-up approach, the other is top-down approach. Now I want to discuss about different approaches and the advantages and disadvantages of these two approaches. The bottom-up approach is the basic and main approach for measurement uncertainty. This approach identifies different stages in the analysis from the beginning. For example, starts from sampling and then extraction, sample preparation, then digestion, or any other steps that are required. And for each stage, this method identifies the different components of uncertainty. Then combine all these uncertainty sources together and give a combined uncertainty value. This method calls bottom-up approach. This bottom-up approach has some advantages. For example, when the laboratory is identifying all the stages of the method and then identifies the component of uncertainty in each stages, so the laboratory can, at the end of the calculation procedure, can notice that which step has the most effect on the total uncertainty. So the laboratory can optimize the method by optimization of these stages of the method. The other advantages of bottom-up approach is that this method gives the real estimate of laboratory uncertainty. This is the procedure of the laboratory. The laboratory has identified all the sources of uncertainty during the procedure. So this calculated uncertainty or estimated uncertainty value is the real estimate of laboratory uncertainty. The other advantages that is very important for laboratories is this method helps the laboratory in training of new employed personnel. When the laboratory estimates the measurement uncertainty using bottom-up approach and knows the sources of uncertainty at each stage of this method, so when hiring new personnel in the laboratory can emphasize on these stages and ask the new personnel to perform these stages of the method more effectively. But bottom-up approach has some disadvantages. For example, there are lots of sources in the measurement procedure for calculating the uncertainty. When the laboratory forgets one of these approaches, the value, the combined value at the end of the calculation procedure will be affected directly. The other disadvantages is that this method is very time consuming. The laboratory should go through all the components of the laboratory, perform the calculation and some statistical analysis to get the combined value. So it is very time consuming for the laboratory. But despite all these disadvantages, most of the guidelines and standards and books recommend bottom-up approach. The other approach, this is, we can say it's a new approach, is top-down approach. As we can see in this slide, the top-down approach says that the uncertainty, which is here, expanded uncertainty at the end, only has two sources of uncertainty. One of them are systematic errors, the other ones are random errors. So this method doesn't go through all the details of the measurement procedure. It just goes through the sources of systematic errors and random errors. This slide, this algorithm, shows different methods to calculate these systematic errors or random errors. For example, the laboratory can use certified reference materials to calculate the laboratory bias. So by calculating the laboratory bias, the systematic uncertainty can be calculated. On the other hand, for random errors, the laboratory can use the control charts. For example, laboratory quality control activities that perform every day. The laboratory can use the control charts data, the standard deviation, reproducibility standard deviation in the laboratory to calculate the random error for calculating the uncertainty. So these sources can be combined together, and now at the end we have combined standard uncertainty. Different approaches can be seen here, for example, using certified reference material, or for example, participating in proficiency testing programs, or using the recovery activities are methods to calculate the systematic error of uncertainty. On the other hand, we have random errors of uncertainty. For example, as we said, using the control charts on the routine sample and the samples that are from the same matrix of the routine sample, or for example, duplicate analysis on routine sample or the control charts on the reference standard. These are different approaches for calculation of measurement uncertainty, random error, or systematic errors. The top-down approach says that the laboratory is doing the quality control activities, method validation activities every day, verification activities in a routine basis. So the results of interlaboratory studies can use to estimate the measurement uncertainty. But this is an issue. The laboratory should have satisfactory results in the interlaboratory or proficiency testing programs. The other way to calculate the measurement uncertainty using top-down approach is using the method validation studies. During the method validation, the laboratory gets some estimation about random errors and systematic errors. So the laboratory can use these results to calculate the measurement uncertainty. There are some advantages and also disadvantages for top-down approach, as we can see in this slide. For example, this method is much simpler because there is no need to go through all the details of the measurement procedure. And also, it's cost-effective approach because there is no need to perform more replicate analysis again. The laboratory has performed the quality control activities, has performed the quality control chart, the laboratory has control chart data, so there is no need for more measurements, so it's more cost effective. But on the other hand, one of the disadvantages of this approach is that this uncertainty doesn't give the laboratory the information about the influence of each steps of the measurement. As we saw in previous slide, we only have two sources of uncertainty, random and systematic components. So at the end, we cannot know which component or which sources of uncertainty during the measurement procedure has more effect on the uncertainty. So the laboratory cannot improve the method after calculation of uncertainty using this method. But this method is rapidly expanding in number, and so there will be a hope that this method will be a real alternative to bottom-up methods, because the bottom-up approach is very time-consuming. Laboratories who are seeking for international accreditation maybe does not have enough time to go through all the details of the method. So there will be a hope that this method will be take place of the bottom-up approach. But it has another disadvantages also, this top-down approach, that the sampling uncertainty sources cannot be seen during this method, because we only go through the random error and systematic error during the measurement activities, not the sampling. So these sources of uncertainty cannot be seen in the measurement. So that would be a reason that this calculated uncertainty cannot be real for the laboratory. But as we said, there are advantages and disadvantages for bottom-up approach and top-down approach. But for conclusion, we can say that since the laboratory wants to know the estimate of the uncertainty, and as we have seen in many standards and guidelines, this is the estimation of the uncertainty. So all the measured value of uncertainty is an estimate. So the top-down approach may be very useful for all the laboratories who are just going to take the accreditation and 17025 laboratory accreditation certificate. And bottom-up approach is very good for the laboratories who are going to improve the methodology of the method, maybe the research and development laboratories or the laboratories who want to optimize the methods. The bottom-up approach will be very useful. Okay, thank you for your attention. If you have any question, I can answer your question.
Thank you, Bahar, for this very informative presentation. Now, with the time left, we will go ahead with questions. Therefore, if you have any questions, it's time to ask them. Please use the comment box or the raise hand function. Thank you. I have a hand raised here from Shiranji. I'm going to go ahead and unmute you, and you can go ahead and ask your question directly to Bahar. I have unmuted you, so you can go ahead and ask your question. You can go ahead and ask your question if you are ready. I have unmuted your mic. It seems that we're unable to hear the attendee. You can go ahead and write your question in the question box, and I will read it out to Bahar. Until then, I will go ahead and I will move on to the next question. The next question is, in your practical experience, which approach, bottom-up or top-down, have more beneficial value in measurement for organizations?
As I have seen in different laboratories, it depends on how the laboratory would like to use this uncertainty value. If the laboratory just want to have an estimate about the uncertainty, the top-down approach will be very useful. But it also depends on the specification of the products that the laboratory is going to give reports to the customer. According to the specification of the customer, maybe the top-down approach will not be suitable for the laboratory, because in most of cases the top-down approach value is a little bit bigger than the bottom-up approach. So the laboratory should see that's how they want to use this measurement uncertainty value.
Thank you. The next question is, Can you please provide some examples how measurement uncertainty can benefit an organization's risk assessment?
Yes, during the risk assessment, the laboratory should identify all the sources of the risk. So when the laboratory is going to estimate the uncertainty, the first step in estimating the uncertainty is identifying the sources of uncertainty. After this identification, most laboratories use the fishbone technique to identify the sources of uncertainty. And after that, for risk analysis, I think the top-down approach might be very useful, because at the end of this approach, the laboratory can see which sources has more effect on the measurement uncertainty. So according to these values, the laboratory can go through these sources and perform some actions to reduce the risk of these sources in the laboratory.
Thank you. The next question is, in your experience, what should in practice laboratories implementing ISO 17025 focus on when implementing uncertainty measurement?
Sorry, could you please repeat your question?
Of course. The question is, in your experience, what should, in practice, laboratories implementing ISO 17025 focus on when implementing uncertainty measurement?
Sorry, I didn't get the meaning of this question. The question is, what should they consider during the implementing of 17025 in the laboratory?
I believe the question could be that when you implement 17025, during the implementation, in practical terms, what should they focus on when they take into consideration uncertainty measurement, is what I'm guessing the question is.
I think the laboratory should consider all the quality control activities, and they should have an established plan for method validation, because the method validation and verification and also quality control activities and also the equipment management should be considered during the measurement uncertainty in the laboratory. I think these topics are very important for establishing this standard in the laboratory and also for calculating the measurement uncertainty.
Thank you. I have someone that wants to ask a question, and hand raised. I will go ahead and unmute your mic, Danielson Moda. You can go ahead and ask your question. I have unmuted you.
Hello.
Hello, we're able to hear you. You can go ahead and ask your question.
Yes, it's the same like they asked it before. It's okay now.
Your question has been answered. Is that right?
Yes, it's been answered.
Okay, thank you very much. If you have any other questions, we can unmute your mic again, or you can write your question in the chat box. Thank you. The last question that I have here, Bahar, is how can the ISO 17025 standard help when it comes to measurement uncertainty in different industries or organizations, is the question.
How the measurement uncertainty can help the laboratories?
Yes.
Sorry, could you please repeat your question again?
How can the ISO 17025 standard help the organization or industry when it comes to measurement uncertainty being used, is I believe what it's saying.
Okay. Yes, okay, got the question. According to 17025 standard, one of the main requirements in this standard is estimating the uncertainty. So when the laboratory is going to get this certificate, the laboratory is forced to calculate and estimate the uncertainty. So it will be a tool for the laboratory to perform some measurements and some statistical analysis to get the value about the uncertainty.
Another question that has just been raised is, what have organizations mostly encountered as difficulties when doing this?
One of the most problems that laboratories have encountered during the measurement uncertainty calculation is the time-consuming method, the bottom-up approach, as we discussed. It is very time-consuming. For example, the laboratory has about 30 test methods in the accreditation scope. So they want to calculate the uncertainty for all of these test methods. And most of the time they don't have enough time to go through all these calculations. One of the main problems they have is the limited time that they have encountered. And I think the other problem is that this method needs that the laboratory should perform many replicate measurements. It doesn't matter with which approach the laboratory wants to calculate the uncertainty. The laboratory should have quality control data. The laboratory should be very well established in quality control activities and method validation activities. And it needs the time and reference material and also personnel to perform these analyses in the laboratory.
Thank you again, Bahar, for this clear and informative presentation. Because of the time limited, we will have to conclude this presentation. However, if you have any other questions, you can send your questions through email and we will answer to them individually. I want to thank all the attendees as well for taking time out of your busy schedules to join us today. We hope you enjoyed the webinar. To keep up with our webinars, please check PECB's webinar schedule on our website, pecb.com, or our official social media network. Next week, we are organizing webinars on interesting topics. Next Tuesday, we are hosting a webinar on the topic Market Segmentation, a Customer Critical Success Factor Development Criteria. Thank you, Bahar, and thank you, everyone.